You've probably heard all the hype about AI that can teach itself, right? That it just keeps getting smarter and smarter all on its own. But here's a question. Is it actually learning to think in new ways, or is it just getting really, really good at what it already knows? Well, today, we're going to dig into some fascinating research that puts that very idea under the microscope.
I mean, we've all seen the headlines. Think about an AI like AlphaGo. It started with just the basic rules of the game Go and ended up discovering strategies that no human had ever even conceived of. And that's the dream, right? That we could apply that same magic to AI for things like math and coding and let them just self-improve their way to superhuman levels of reason.
But this brings us to the core of the issue. When we see an AI getting better and better at a task, is it actually discovering brand new abilities? Or is it just getting way, way faster and more efficient at using the knowledge that was already baked in from the start?
So the main technique behind all this self-improvement talk is something called reinforcement learning with verifiable rewards, or let's just call it RLVR. The concept is actually pretty simple. You give an AI a problem, like a math problem. If it gets the right answer, you give it a little reward, a virtual pat on the back. You do this millions and millions of times, and the theory is the AI should learn to get more rewards by, well, getting more answers right.
For a long time, the popular belief in the AI world has been that this process does way more than just reinforce good answers. The thinking was that through all this trial and error, RLVR was actually helping the AI discover fundamentally new ways to reason, pushing its own boundaries far beyond what it could originally do.
But is that what's really happening? Researchers at Leap Lab at Tsinghua University decided to put this whole idea to the test. They asked a simple question: is RLVR really the engine of discovery we all think it is? And to find out, they realized they needed a whole new way to measure an AI's true potential. And this is where it gets really clever. They used a tool called the Pass@K metric. Now, instead of just asking, did the AI get it right on the first try, Pass@K asks something much deeper. It asks, look, if we give this model K chances, say 100 or even 1,000 attempts, can it solve the problem even one time? This completely shifts the focus from just, average performance to the absolute outer limits of what the model is capable of.
So here's the breakdown of how it works in practice. Super simple. You give the AI a problem, you let it spit out, let's say, 100 different solutions. Then you just check, are any of those 100 solutions correct? If even just one of them hits the mark, we call that a pass. This tells us if the right answer was even in the model's universe of possibilities, even if it wasn't its first guess.
Okay, so this sets up the million-dollar question. What happens when you take a standard, off-the-shelf base model and put it head-to-head with a model that's been through tons of this RLVR training? Using this new metric, which one actually has more potential? The answer is, well, it's not what you think. And here are the results. And honestly, they're completely counterintuitive. Take a look at this chart. On the far left, where you only get one attempt, the RLVR-trained model is the clear winner. No surprise, right? It's been trained to be good on the first try. But watch what happens as you move to the right, as you give both models more and more chances. The curve for the original, base model just shoots up, eventually crossing over and leaving the trained model in the dust. With enough attempts, the original, untrained model actually solves a wider range of problems. It's wild.
So let's just break that down, because this is the absolute key finding. The RLVR trained model, yeah, it's better at giving you the right answer on its first go. It's more efficient. But the base model, the one without all that extra fine-tuning, can actually solve a broader variety of problems if you just give it enough shots. Its potential is just bigger. The researchers themselves, they don't mince words. They put it bluntly in their paper, saying that instead of expanding the AI's mind, current RLVR training can actually make its reasoning scope narrower. It becomes a specialist, sure, but it loses its general problem-solving ability.
Here's a great way to visualize what's going on. Think of the base model on the left as this big, bushy tree, exploring all sorts of possible paths to get to a correct answer. The RLVR model on the right, well, it's been pruned. The training reinforces a few really strong, reliable branches to the answer, but in the process, it just cuts away all these other potential solutions, narrowing its whole approach.
Okay, here's an even simpler analogy. RLVR basically turns the AI into a musician who rehearses their one-hit single over and over and over until it's absolutely flawless. They can play it perfectly every single time. The problem? They've forgotten how to improvise. They've forgotten how to explore or how to play any other song. The base model is more like that musician who might mess up a few notes, but they still know a whole library of chords and styles to draw from.
And if you're a numbers person, the hard data really tells the story here. This table shows the overlap on a math dataset. Check out that top left box. Of all the problems the fancy RLVR model can solve, a whopping 92.4% of them were already solvable by the original base model. Now look at the top right box. The RLVR training only taught the model to solve a tiny 1% of new problems. This just screams that it isn't discovering much that's new, it's mostly just optimizing what it already knew how to do.
So this all leads to a pretty huge question, right? If this super popular method, RLVR, isn't really a discovery engine, then how can an AI learn genuinely new ways to reason? Is there another way to do it?
Well, it turns out the answer is yes, but it requires a fundamentally different approach, something called distillation. And to put it simply, distillation is basically like having a smarter teacher model show a student model the ropes on how to solve problems.
And wow, the results from this method could not be more different. This chart shows that the distilled model, the student that learned from a teacher, is just consistently and significantly better than the original base model, right across the board no matter how many chances you give it. Unlike RLVR, this method actually expands the AI's core capabilities.
So at the end of the day, we're looking at two totally different paths to AI improvement. RLVR is all about sharpening what's already there, making the model a faster, more efficient version of itself. Distillation, on the other hand, is about transfer. It's about giving the model genuinely new knowledge and new skills from a more powerful source.
All right, so let's boil this all down. What are the big takeaways from all this? First, and most importantly, current RLVR is an optimization tool, not a discovery engine. Second, it makes AI more efficient, for sure, but it can come at the cost of narrowing its reasoning. Third, this means an AI's real potential is often limited by its starting point, that base model. And finally, if we really want AI to truly discover things on its own, we're probably going to need entirely new methods that go beyond what we're doing today.
And that leaves us with one final, fascinating question to chew on. If just rewarding right answers isn't enough to create new ideas, then what kind of exploration, what kind of freedom, or even chaos will an AI need to truly have an original thought, to discover something that no human and no teacher model has ever shown it before?